Hello friends, in this video we're going to solve this question. Find the Laurent series of this function about z is equal to 0 and about z is equal to 2 separately, and from the series that we're going to obtain that Laurent series, okay, we need to verify that z is equal to 0 is a pole of order 1 and z is equal to 2 is a pole of order 3. Also we need to find the residue of the function, given function f of z at its pole, right? So before we solve this question, please do watch the videos that I have given in the description box. I have given two links of two videos. One is about singularity and pole, and another is Laurent's theorem, okay, Laurent series, and I have given the link in the description box, okay. I have already solved, I have already given few examples on this topic. I have given the links in the description box. Please do watch those two videos, okay, and please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. If you want to follow me on Insta, this is my Insta ID, OJHALAKHYAZIT123. that's my Insta ID. You can follow me on Insta, okay. So now let's start. So here is the given function we need to find. We need to find Laurent series about z is equal to 0 and z is equal to 2, okay. First let us find Laurent series about z is equal to 0. About z is equal to 0, we need to find a Laurent series about z is equal to 0. First let us find about z is equal to 0. Now you see, so if we need to find the series about z is equal to 0, then we need to express the series as a powers of z, okay. And if we need to find the series about z is equal to 2, then we can write z minus 2 is equal to 0. Then we have to express the series at z as a power of z minus 2, okay. But for z is equal to 0, we're gonna express the series as a power of z, okay. So now how to do that? First let me write the given function. Fz is equal to 1 by, let me write the given function here. The given function is this: 1 by z into z to the power, sorry, z minus 2 whole to the power 3. 1 by z into z to the power z minus 2 whole to the power 3, okay. So this is the given function. So now you see it can be written this way, that 1 by z into z minus 2 whole to the power 3. Now we have to take common 2. Actually we're going to take minus 2 common from here. Now you see z minus 2, if you actually we have to express this in terms of 1 minus x to the power minus n or plus n, okay. So it may be minus 1 or plus 1, okay, 1 plus x or 1 minus x, okay. We're gonna expand that, okay. So for that, x minus z, if we z minus 2, if you take minus 2 common, then it will be 1 minus z by 2, okay. And remember one thing, always take the common in such a way that here you get 1 and here you get z by 2 or whatever be the number here, okay. But don't get it like this, 2 by z, okay. You don't need to get this one, okay. That will be wrong, okay. Remember that. So now you see, once you have taken common this, if we have whole cube here, then here should be also cube. So that means we're going to take minus 2 whole to the power 3 common here, 1 minus z by 2 whole to the power 3, okay. So that's why it can be written 1 by z into minus 2 whole to the power 3 into z, sorry not z, 1 minus z by 2 whole to the power 3. Okay, now it can be written this way, that 1 by z minus 2 whole cube, that's going to be minus 8, so minus 1 by 8z 1 minus z by 2 whole to the power minus 3. We can write that way, right? Hope you have understood this. So now you see, we know this series, expansion of this series, 1 minus x whole to the power minus n, and that's equal to, expansion of this is 1 plus n into x plus n into n plus 1 by factorial 2 x square plus n into n plus 1 into n plus 2 by factorial 3 into x cube plus dot dot dot, so on. If we use this expansion to expand this, here we're gonna take a minus 3 as minus n. Okay, we're gonna take minus 3 as minus n and z by 2 as x, right? And if we take that, then what we're gonna have, 1 plus, instead of n we're gonna write 3. Okay, instead of minus n we have minus 3, so n is equal to 3 here, into x is z by 2 plus n into n plus 1, that means 3 into 3 plus 1 means 4, 3 into 4 divided by factorial 2, factorial 2 means 2 into 1, so you can simply write 2 into 1 into x square, that means z square by 4, z by 2 whole square, that's going to be z by 4, right? Plus then again 3 into 3 plus 1 means 4 into 3 plus 2, that means n plus 2 here, 3 plus 2 means 5, okay, divided by factorial 3, that means 3 into 2 into 1 here into x cube. X cube means z to the power 3 by 8, 2 cube is 8 plus dot dot dot, so on. Okay, so that's how we get. So now you see here it's supposed to be, so here we should write minus 1 by 8z, I forgot to write that one. Okay, now here you see. Okay, so what we will get after cancellation, so here 4 cancel, and here you see what we have. Okay, here 3 cancels, and 4 cancels 8 gives 2, okay, and so on. So here we're gonna have minus 1 by 8z 1 minus z by 2 whole to the power minus 3. So this expansion is equal to actually 1 plus here 3z by 2 plus 3z square by 2, then plus we get here 2 into 2, that's going to be 4, 5 z cube by 4, right, and so on, right? Now you see, if we multiply this 1 by z with those, then what we're gonna have, let me multiply that, minus 1 by 8, here we're gonna have 1 by z plus 3 by 2 by z cancels. Okay, if you multiply 1 by z with this, these two z will be cancelled, and if you multiply 1 by z with this, then z square cancel by z, so we're gonna have 3z by 2. Okay, then next we're gonna have 5z square by 4 plus dot dot dot, so on. That's how we're gonna have. So this is the required Laurent series. So this is the required series. Okay, this is the required Laurent series. Okay, now let me show that z is equal to 0 is a pole of order 1. Okay, so now let me copy this series, this Laurent series that we have got, and let me write on the other side to show or to verify that z is equal to 0 is a pole of order 1 from the series as given in the question. So let me write the series this way. Now here you see, let me tell you one thing. We know that if z is equal to a, okay, is isolated. If you don't know singularity, isolated singularity and non-isolated singularity, do watch the videos given in the description box. Okay, isolated singularity or singular point of f of z, then its Laurent series of this f of z can be expressed as a0 plus a1 z minus a plus a2 z minus a whole square plus dot so on, then plus b1 by z minus a plus b2 by z plus a dot plus bm by z minus a whole to the power m plus dot so on. Now here you see, if the next term of this term bm plus 1 by z minus a whole to the power m plus 1, if that term is equal to 0, in that case we call z is equal to a is a pole of order m, right? Pole of order m, right? So here we can write, if bm plus 1 by z minus a, or simply you can write if the constant bm plus 1 is equal to 0, right, then z is equal to a is a pole of order m. Now here you see, this, in this case, this z is considered to be z minus 0, because we are going to find the we are going to verify that z is equal to 0 is the pole of order 1, so that's why. Okay, and this term should be considered as z minus 0 whole square. That means we're going to compare with this z minus a whole square, right, and so on. And the term, this b1 by z minus a, that will be compared with this. Here 1 by z means this is 1 by z minus 0, so it can be compared with b1 by z minus a. And here 1 by z minus 0 whole square, this term is 0, actually this term is missing. That means here we have b2 is equal to 0. Okay, if b2 is equal to 0 here, so that means this z minus a is a pole of order 1, right? Here a is nothing but 0, right? Hope you have understood this. So here b1 by z minus a is equal to 1 by z, which means 1 by z minus a z minus 0. And here this b2 by z minus a, this term is missing. This z minus a whole square, this term is missing. That means here b2 is equal to 0. Here we can say this term is 0. Okay, therefore z minus a, which is z minus 0, therefore z is equal to 0 must be the pole of order 1, right? That must be pole of order 1. Now let us find the Laurent series about z is equal to 2. Okay, so now let's find the Laurent series about z is equal to 2. Okay, so let us put z minus 2 is equal to t. So we're going to put z is equal to t plus 2, and then the function becomes f of z is equal to 1 by, instead of z we're going to write t plus 2, and this instead of z minus 2 we're going to put t, right? Z minus 2 means here t, so here we will write t. So our motive is to express the series in terms of powers of z minus 2. Then we're going to get the Laurent series about z is equal to 2. Okay, so now you see here z minus 2 is t here. Okay, this is t cube. Now we can write this as 1 by t to the power 3, and we can write this one t plus 2 whole to the power minus 1. We can write this way. Okay, again if you take before that you can take 2 common actually, right? Let me do one more step. If you take 2 common, right? If you take 2 common, you're gonna get 1 plus t by 2 to t cube. That's what we're gonna have, right? T by 2. Okay, so we can write this in this way: 2t cube 1 plus t by 2 whole to the power minus 1. That's what we're gonna have. Now you see f of z 1 by 2t cube. So how to expand this? We're going to use this 1 plus x whole to the power minus 1. Okay, we know that 1 plus x whole to the power minus n is equal to 1 minus nx plus n into n plus 1 divided by factorial 2 x to the power 2, then again minus n into n plus 1 into n plus 2 divided by factorial 3 into x cube, then plus again so on. So wherever you see odd power on x, put minus before the term, right? Okay, hope you have understood this. Now you see, so here we're going to consider this t by 2 as x, okay, and minus n as minus 1. Okay, that means n is equal to 1 here. So if we apply that formula here, we're gonna get 1 minus n is 1. So here instead of x we're gonna put t by 2. So we're gonna replace x is x by t by 2 and n by 1. Okay, in this series, in this expansion, then we're gonna get the expansion of this, right? So hope you have understood this. If we do so, then what we're gonna have here, 1 into 1 plus 1, that means 1 into 2. 1 into 2 means simply 2. Factorial 2 means 2 into 1, and then x square is t square divided by 4, right? So here 2 cancels. The next term is minus n into n plus 1, that means 2. Here n is 1, so then n plus 2 is 3. Okay, then 1 into 2 into 3 divided by factorial 3. Factorial 3 is also, you know, 1 into 2 into 3, that means 3 into 2 into 1, that is factorial 3, right? X to the power 3 means t cube by 8. So here these numbers are also cancelled. Okay, hope you have understood then. Plus dot 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 so on. So here we're gonna get 2t cube 1 minus t by 2 plus t by 4, t square by 4, then minus t cube by 8 plus dot 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 so on. That's what we're gonna have, right? Hope you have understood this. Now you see, let's multiply 1 by t cube with this series. Then what we're gonna have, 1 by 2 1 by t cube minus, if we multiply this one with this, then t cancels t cube to gives 1 by 2 t square, plus then if you multiply this one and this one, t square cancels t cube to give 1 by 4 into t, then minus, if you multiply this one with this, then t cube will be cancelled, we're gonna have 1 by 8. Then if you multiply this one with next term, so here next term of this series should be like this. That's supposed to be, you know, t to the power 4 by 16. Okay, so if you multiply with that, then you're gonna have t by 16. Okay, then minus, you're gonna have t square by maybe, sorry, that's t square by 32 and so on, right? That. So now you see, again we're gonna use this concept. Here you see, we're gonna use this concept, right? So let me copy these things. So first, instead of writing all this, okay, so let me copy these things. So just let me take a new slide. Okay, let me take a new slide and let me write the expansion f of z. Let me copy this expansion as well. So here is the expansion. Now here you see, so let me clean this things. Okay. Now here you see, this a naught is 1 minus 1 by 8. A1 z minus a is nothing but this one. So here you see, let me do one more thing, that is, here you see, just give me a second. So this t is nothing but z minus 2, right? So we're going to replace t by z minus 2. Then what we're going to have, 1 by 2 into 1 by t cube means z minus 2 cube minus 1 by 2 into z minus 2 square plus 1 by 4 into z minus 2 plus 1 by 4 into 8 into nothing is there, so here no z is there, right? Plus here z minus 2 by 16 plus dot 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 so on. Okay, here you see, so here you can see these terms are respectively this. Okay, if you compare these two series, okay, so this one should be considered as this one, right? Then this one should be considered as this, and this and so on. Now this term should be compared with this next term, that is here it is b2, the next term will be b3 by z minus a whole square plus dot 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 this. Okay, so now here this term is missing. b4 is equal to 0 in this series, right? b4 by z minus 2 whole to the power 4, that is missing here. So that's why we can say b4 is equal to 0 here. So here we will get 1 by z minus 2 whole to the power 3 is equal to b3 by z minus a whole to the power, here it's supposed to be 3, just give me a second, whole to the power 3, and b4 is equal to 0 here. So that's why, therefore, according to this, if z is equal to a is isolated singular point of fz at then we can express the series this, and if bm plus 1 is equal to 0, then z is equal to a is a pole of order m. If bm plus 1 is equal to 0, here b4 is 0, that means b3 plus 1 is 0. So that's why z is equal to 2, z is equal to 2 must be pool of order 3, right? Hence verified. Okay, hope you have understood this. Now we need to find the residue at z is equal to 0 and at z is equal to 2. Okay, now let me take a new slide. Now we need to find the residue at z is equal to 0, and z is equal to 0 is a pole of order 1, that means it is a simple pole. Okay, how to find the residue at simple pole? Okay, so you know, if z is equal to a is a simple pole, then residue of the function f of z at a is given by limit z tends to a z minus a into f of z. Okay, so you can apply that. So here you see residue at, you know, residue of this function f of z at z is equal to 0, that's going to be equal to limit z tends to 0, then z minus 0, then f of z, right? So here limit z tends to 0, z minus 0 means simply z, f of z is nothing but 1 by z into z minus 2 whole to the power 3. Here z cancels, so limit z tends to 0, 1 by z minus 2 whole cube. If we evaluate this limit, then we're going to have 1 by minus 2 cube, that's going to be minus 1 by 8. So this is the residue at z is equal to 0, right? This is the residue at z is equal to 0. Now let us obtain the residue at z is equal to 2. Okay, let me go to the next page, right? Now here you see residue at z is equal to 2. Here this is a pole of order 3. Now you see, so how to find the residue at pole of order n. So how to find that residue at z is equal to a? Suppose this is a pole of order a. In that case, how to find that residue at f of z, which is z is equal to a, okay, which is a, you know, pole of order n. In that case, 1 by n minus 1 factorial curl bracket and n minus 1th order derivative, okay, n minus 1th order derivative with respect to z of let me write here, just give me a second. Of here z minus 2, sorry not 2, z minus a, if the pole is z is equal to a, whole to the power n, whatever be the order of the pole, then f of z, right? That's how we used to find it. So here n is equal to 3, okay, n is equal to 3 and a is equal to 2, okay, a is equal to 2 here, this is a, okay. So therefore here residue of f of z at z is equal to 2 will be given by 1 by, as it is order of 3, so that's why we're going to take, instead of n minus 1 factorial, here we're going to take 3 minus 1 factorial. That means we can write 2 factorial, right? Then order is n, so derivative should be taken n minus 1th order. So here order is 3, so we have to take second order derivative with respect to z of z minus 2, and order is 3, so here we're going to write cube, okay, we're going to write cube here. Then f of z is here 1 by z into z minus 2 cube, right? This is f of z, right? Hope you have understood this, because the given function is which is f of z, sorry, so the given function is f of z is equal to 1 by z into z minus 2 whole cube. This one is the given function. So here you see this 2 cancels, so we have 2 factorial means 2, right? Second order derivative with respect to z of here 1 by z, right? Now 1 by z means we can say z to the power minus 1. If you differentiate it with respect to z, then you should get minus 1 into z to the power minus 1, that's gonna be minus 2, right? So for second order derivative you have to differentiate it again, then what you gonna get? So minus 2 minus 1, that's gonna be plus 2, then z to the power minus 3, that's what you're gonna have, okay. So therefore we're gonna have 1 by 2 into z to the power minus 3. So we are going to obtain the residue at z is equal to 2, so we have to put 2 here, z is equal to 2, okay. Here we have to write z is equal to a in this case, right? So at z is equal to 2, right? So now you see then what we're gonna have here. So let me simplify this. So 1 by 2 and 2 into z to the power minus 3 means 2 to the power minus 3 in this case, right? And this 2 cancels, 2 to the power minus 3, okay, this is supposed to be 2 to the power minus 3, and 2 to the power minus 3 means 1 by 2 to the power 3, which is nothing but 1 by 8. So this is the residue at z is equal to 2, right? Hope you have understood this. Thank you for watching. See you in the next video. Bye bye.